In this video, we'll be looking at cylinders and quadric surfaces. In particular, we're going to define the term cylinder for our class. We'll talk about what a trace of a surface is, and we're going to discuss one of the quadric surfaces, which is ellipsoids. We'll do the other quadric surfaces in another video. So let's talk about the surfaces that we've studied so far. In this class, we know of two surfaces. In the first section, we talked about spheres. They have this equation: x minus x naught squared plus y minus y naught squared plus z minus z naught squared is r squared. And that was derived using the distance formula. So imagine you're in three-dimensional space. Go out to some point x naught, y naught, z naught. Make a little rectangular box to give me some sense of perspective here. So this is, we go x naught units in the x direction, y naught units in the y direction, z naught units in the z direction. So that's our center, x naught, y naught, z naught. And then we go r units in all directions. So we're going to go forward r units and backwards r units. That's the x direction. And left r units and right r units in the y direction. And then up r units and down r units in the z direction. And that's going to give us our sphere. It's hard to draw. So we're just going to draw a cartoon. We're going to draw something that looks like a sphere. And we'll say that's good enough for us. And to indicate the radius, I'll just put a little vector in there. It starts at the center and goes out to a point on the sphere. And we've got a sphere of radius r. So if you see something that looks like this, you know that it's a sphere and its radius is r. So for example, if I have x plus 1 squared plus y minus 3 squared plus z minus 4 squared equals 25, then I can read off the center. We did this in a different video as well. The center is x naught, y naught, z naught. Now remember, the coordinates of the center have the opposite signs of the numbers that you see here. So if I see a plus 1, x naught is minus 1. If I see a minus 3, y naught is plus 3. If I see a minus 4, this is 4. And then this, remember, is the radius squared. It's not the radius, but the radius squared. And so if I want to get r by itself, and r is a distance, so it's the positive square root, we find out that r is 5. So we could plot this point in three-dimensional space. I'm just going to label it -1, 3, 4. And then we're going to go 5 units in the x direction, y direction, and z direction. It's a little hard to do, so I just draw a circle around that point with a line for dimension, and I'll just say, hey, r equals 5. And that's good enough for us. And if we want a coordinate system, that can tell us where that is relative to the origin. So we could always add that too. So we know about spheres. We also know about planes. We studied planes in the last section. Remember, if a plane passes through the point x naught, y naught, z naught, so we're certain this is a point in the plane, and those are given. And it has a normal vector n with components a, b, and c. Standard form of the equation of the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. That's standard form. Now, if we distribute and collect like terms, and move the constant to the other side, we get this equation. Some books call this general form of the equation of a sphere. I've also seen the equation of the sphere with the constant on the left-hand side. So other books call this general form. And of course this D here, and put a little subscript star on it, this D is different from that D. They're just opposite of each other. So if I see something like this, if I see x plus 2y plus 3z equals 7, well, I know I've got x raised to the first, y raised to the first, and z raised to the first. It's equal to a constant on the other side. So that is a plane. And its normal vector is given by the coefficients of x, y, and z. Remember, these are the components of our normal. So the components of our normal appear here in general form. So I see a 1, a 2, and a 3. So this normal vector is 1, 2, 3. And if I want a point on this plane, I can choose y and z to be any values I want, and x is automatically given by the equation. You can actually pick any two variables to be any value you want, because this is going to be well defined for all x, y, z, or not all x, y, z, for any x, y you choose, and then z will be determined by this equation. Or I could choose y and z, and x would be determined by this equation. Or I could choose x and z, and y would be determined by this equation. So there are lots of points in the plane, infinitely many points. If you want one of them, I would do this, just set y and z equal to 0, because it's the easiest. If y and z are 0, we get x equals 7. So if I need a point in the plane, x, y, z equals 7, 0, 0 will work. So I see this, and I think plane. I see this where x, y, and z are all squared. There's nothing under them, just an implied 1, and a constant, a positive constant on the right-hand side, and I think of a sphere. So we know how to identify the center and the radius from the standard form of the equation of a sphere. And we know how to identify the normal and find lots of different points on the equation of a plane. Or on the plane itself, excuse me. So those are the two types of surfaces that we know so far. We've got spheres and planes. Now let's add another surface. I'm going to call it a cylinder. Now it's not exactly the cylinder that you're expecting, although the cylinder that you're probably expecting is a cylinder. It's a special case of this. When I think of a cylinder, or when most people think of a cylinder, they think of something that looks like this, a right circular cylinder. It's supposed to be a circle. So the base is a circle with a radius r. It has some height. And that's what we're used to. This is a right circular cylinder. Oops. Okay. Now in our class, the definition is a little bit more general. So here it is. We're going to let C be a curve. It's in some plane. And L is a line that is not in a parallel plane. So for simplicity, let's say C is in the xy plane. And maybe our curve C looks like this. And L is not in a plane with z equal to a constant, because down in the xy plane, remember, z equals 0. I don't want a line at the level of z equals 1 or z equals 10. I want a line that is not in a plane like that. So it has to have some z component. If its direction vector does. So I'm just going to draw a line. So let's say we have a line like this. This is a line L that's not in a parallel plane. Then the set of all lines parallel to L and intersecting C is called a cylinder. That's what we mean by cylinder in our class. So here's my L. I'm going to draw a bunch of lines that are parallel. Oh, that does not look parallel at all, does it? There we go. That's parallel to L, that's parallel to L, that's parallel to L, and so on. And so what we get is, when I take all the lines parallel to L and I intersect them with C, what I see is the curve C is up here as well. Well, I didn't do a very good job drawing exactly the same curve, but I hope you get the idea. Looks like that on one side, and then maybe like this in the front and the other. So this is the side that's closest to us, and that green side, that's in the back of the cylinder. So basically I've got like this peanut shape and the same shape over here. And these are all the lines that are parallel to L. And then these other ones, they kind of go behind us. I'm not doing a very good job with these pictures. I hope you get the idea. So I've got basically this C shape that's just repeating itself forever along this line L, parallel to L. So this would actually continue. There would be another one of those C's up here and another one up here, and then there's another one below us. The cylinder is all of those lines together. So this cylinder is just a special case of this. Before we go on to that, the parallel lines, these lines that are parallel to L that intersect C, are called rulings. And we're not going to look at cylinders like this, where the line L is not parallel to one of these axes. In our class, we're going to look at right cylinders. With a right cylinder, all the rulings are going to be parallel to either the x-axis, the y-axis, or the z-axis. So basically the line is going to be one of the axes, not just some other line. There we go. So when we look at this equation, x squared plus y squared equals 9, back in pre-calculus, we knew that to be the equation of a circle. Oops, that's a y and that's an x. Now comparing that to standard form of the equation of a circle from pre-calculus, the number that we're subtracting from the x and the number we're subtracting from the y in this equation, those two numbers are the coordinates of our center. Since we're not subtracting anything from the x or the y, the center in this circle is 0, 0. And then the radius squared is 9. So that means the radius must be the square root of 9, which is 3. So we would just see this back in pre-calc. And it doesn't have to be perfect. We do the best we can. Oops, there we go, something like that. It's definitely not perfect. So we have a circle of radius 3 centered at the origin. Now, in Calc 3, since this only has two variables, we are going to have a right cylinder. This is what it looks like in the xy plane. But since z isn't on here, z is going to be free to be anything. Now, a lot of students have trouble with this idea, but you've actually done something like this before. Remember in pre-calc or in algebra class, if I said x equals 3, if I wasn't talking about a specific point, but if I was talking about the collection of points where x equals 3, I went over here to x equals 3, and I said, well, when y is 0, x is 3, and when y is 7, x is 3, and when y is negative 2, x is 3. No matter what y is, x is 3, and so we get this vertical line. So when we have x equal to a constant, y is free to be anything. Y can take on any value, and that's going to be on our line. Similarly, if I have y equals 2, and I'm talking about the collection of points where y equals 2, well, that's going to give me a horizontal line. Y equals 2 when x equals 0, and y equals 2 when x equals 3, and y equals 2 when x equals negative 2. It doesn't matter what x is, y is going to be 2. So here, x is free to be anything. That same principle holds in Calc 3. If I am talking about the surface that has equation x squared plus y squared equals 9, so we're in 3D and someone tells you that x squared plus y squared equals 9, they're not talking about a circle. They're talking about our old friend, the right cylinder. They're talking about this guy right here. I say, well, what do you mean, Miss Townsend? Well, this is what it looks like in the xy plane. And that's our generating curve C. So we're going to go 3 units in the x direction, plus or minus 3 units in the y direction. And we're drawing this with a little perspective. It's a little bit hard to do. But that's our base. That's the curve C. And z is free to be anything. So as long as x squared plus y squared equals 9, now z could be 0 like it is down here, or we could go up here to z equals 3, and x squared plus y squared would equal 9. Oh, that was a bad circle. It's supposed to be like that, kind of. Not the best picture. When z equals 4, x squared plus y squared equals 9. So x squared plus y squared equals 9 all the time, and what we end up with, I did a better job with my picture, sorry guys, is a right cylinder. And the rulings, they look like this. The rulings are parallel to the z-axis. And that's exactly what we want. Whenever you have the z variable missing, the rulings are going to be parallel to that axis. It's going to be parallel to the z-axis. Yeah, I've already written that down here. Similarly, here's another surface. If I have z equals y squared, now it's not going to look like that right cylinder, or it's not going to look like that right circular cylinder that we're accustomed to. This actually goes on forever for all z, by the way. But this is going to be a right cylinder as well. Since the x is missing, the rulings are going to be parallel to the x-axis. Here, x squared plus y squared was 9, and z was free to be anything, and so we got this cylinder. Here, z is equal to y squared. So in the yz plane, here's z, here's y. I just see that familiar parabola from college algebra or pre-calculus. But remember, x is free to be anything. So z equals y squared in the yz plane, that's our generating curve C. And if I draw the same curve up here, that's exactly what I would expect to see. When x equals 0, I have that parabola. When x equals 4, I have that parabola. When x equals -4, so it's behind us, I'd have that parabola. And together, if we connect all these points with rulings that are parallel to the x-axis, we get something that looks like that. And I'm going to take my paper and use it as the graph now. So basically what you're going to see is, oops, like a parabola like this. And it's coming out at you. If we're standing over here where x, y, and z are all positive, you're going to see that right there. So this is a cylinder, and that is a cylinder. Since the x was missing, rulings were parallel to the x-axis. Since the z was missing, the rulings are parallel to the z-axis. Here the x is missing, so rulings are going to be parallel to the x-axis again. And I do that because those are going to be easier to draw than the ones that are parallel to the y-axis. But z equals cosine of y. If this is my z and this is my y, we know from trig, well, it's going to oscillate between -1 and 1, right? It's going to keep going. 2 pi, it's there, and then we do it again. And at 4 pi, we're there, and then we do it again. 6 pi, we're over here. But x is free to be anything. So that's when x is 0, that's what it looks like. But when x is 3, we're going to see the same curve over here. You might say, oh, Miss Townsend, that's not a very good graph. You're absolutely right, it's not. Let me try again. So you end up with something that looks like this. And then we're going to see the same shape over here. And I'd say it's still not that great. I know. But let's connect these. Okay. The rulings are parallel to the x-axis. Still difficult to draw. Not quite. It's not obvious what's going on. That's what we're going to see over there, and then that's what we're going to see over there, and that's what you're going to see over there. It's bad. But whenever I see this, you've got this cosine wave here. Z is here, and Y is here, and X is here. It reminds me of lasagna. It's like that wavy sheet. Z is equal to cosine of Y, no matter what X is. So we're going to see that Z equals cosine of Y for all of the X values. And it would just extend more in this direction. But it's still really hard to draw on a 2D piece of paper. So I'm going to say, it just reminds me of lasagna. Because it's easier to visualize that way when I compare it to something I'm familiar with. So those are cylinders. Now, the trace of a surface, something we discussed briefly when we were talking about planes, it's the curve of intersection of a surface with a plane. And in our class, we're particularly interested in traces in the coordinate planes. So we want traces in the xy plane, that's z equals 0, remember, in the xz plane, that's where y equals 0, and then the yz plane, that's where x equals 0. We're going to use these traces to help us visualize these new surfaces that we're studying, which are called quadric surfaces. Now, quadric surfaces are the 3D analogs of conic sections. And their traces in the 3 coordinate planes and planes parallel to those. Z equals a constant, y equals a constant, or x equals a constant. Those traces all turn out to be conic sections. Now, if you don't remember your conic sections, hopefully you covered them at the end of Calculus 2. If it's been a while since Calculus 2, or if your teacher didn't cover it, or if your institution didn't cover it, or maybe you haven't seen these since high school, you might want to go online and search for videos about conic sections, because it'll make the rest of this lecture easier. So let's look at a very simple surface. This one turns out to be called an ellipsoid, and you'll see why shortly. For simplicity, I'm going to center this ellipsoid at the origin. So we'll have x squared over 4 plus y squared over 9 plus z squared, let's say, over 16 equals 1. This is the equation of an ellipsoid. Now, if I want to get rid of the z term in my equation, I can set z equal to 0. And then we've got a new equation, x squared over 4 plus y squared over 9 equals 1. This is the equation of the trace of the ellipsoid that we're concerned about, that we're interested in the xy plane. Alright, so let's figure out what that looks like. In order to do that, we're going to sketch this trace in 2D. Here's our y and there's our x. Now remember from your studies of conics, if you have x minus x naught squared over a squared or b squared plus y minus y naught squared over a squared or b squared equals 1, then you've got an ellipse. And that's exactly what we have here. And it's convention to call the larger of these two numbers a squared and the other one b squared. So we're going to call this 9 the a squared and the 4 the b squared. So this is an equation of ellipse that's longer in the y direction than it is in the x direction. And I know it's longer in the y direction because the larger number is under the y. So basically it's going to have that shape. All right. So let's graph this particular ellipse. Notice we're not subtracting anything from the x or the y. Since we're not subtracting anything from x or y, we get a center of 0, 0. So we're starting right here at the origin. Now a squared is 9. So we take the square root of that to get a. A is 3. Now since the a squared is under the y, and a is 3, we're going to start at our center and go plus and minus 3 units in the y direction. So we're going to go up 3 and down 3. B squared is 4. So that means b is the square root of 4, which is 2. To find other points on our ellipse, we are going to go 2 units, and that's because b equals 2. And this is a b squared and it's under the x. Since the b squared is under the x, we're going to go plus and minus 2 units in the x direction from our center. So we're going to go 2 units this way and 2 units this way. And then you just graph a curve and you get that. That is the trace of our surface, the ellipsoid, in the xy plane. Now we're not ready to graph the whole thing, but now I'm going to take that graph from 2D and go to 3D. So down here in the xy plane, where z is 0, we're going to go plus and minus 3 units in the y direction. So 1, 2, 3, back 2, 3. And then we're going to go plus and minus 2 units in the x direction. So this is an ellipse, it's on an angle. It's a little bit difficult to draw, but that's what our base looks like. Or not our base, but that's what the trace of our ellipsoid looks like in the xy plane. So that's this blue curve that we just came up with over here. Now let's look at the traces in the other planes. Let's let y equal 0 this time and see what the xz trace looks like. So if y equals 0, we had x squared over 4 plus y squared over 9 plus z squared over 16 equals 1. If y is 0, this term is gone, and now we have this ellipse. This is another ellipse. I know it's an ellipse because the x and z are both squared. We're dividing both of these by positive numbers, and they're not the same number. If they were the same number, it would be a circle, and that's set equal to 1. So if our equation can be written this way, or we can manipulate it so that it can be written this way, so that it is written this way, we've got an ellipse. So now let's graph this in the xz plane. Now if you want, you can choose to put the positive x-axis over here. Now I wouldn't recommend that because we're about to go 3D, right? Here's our x that's coming out of the page at us, and y is going off this way. With that in mind, I think instead of putting my x-axis over here, I'm going to put my x-axis here. So I can imagine just taking this whole plane and rotating it towards us so that we would see what it looks like in the xz plane over here. Okay, so we're going to do the same thing as we did before. A squared is 16. And b squared is 4. Forgot to mention the center. We're not subtracting anything from the x or the z. So the center, at least in 2D, is 0, 0. So we're going to start here at 0, 0. Solve for a. Square root of 16 is 4. I'm going to solve for b. Square root of 4 is 2. Now the a squared is under the z. So we're going to go plus and minus 4 units from the center, which is 0, 0, in the z direction. So go up 4 and down 4. and the b squared is under the x, so we're going to go plus and minus 2 units in the x direction. And this is what the trace looks like in the xz plane. And remember, the xz plane is where y equals 0. So we had the xy trace. We went plus and minus 3 units in the y direction. And plus and minus 2 units in the x direction. We had that ellipse. Now in the xz plane, we go plus and minus 2 units in the x direction, so that's here, but we go plus and minus 4 units in the z direction. So we're going to go up 4 and down 4. And that is an ellipse turned on its side. Still a little bit hard to see, but that's back here in the xz plane, so it's parallel to this plane right here. It's in that plane. Okay, and then the last one, we looked at the xy plane, the yz plane, or the xy plane, the xz plane. Now we want to do the yz plane. So x equals 0. So this was my equation. Here x equals 0, so this is gone. And then this is the equation of the trace right there. As you can imagine, it's just another ellipse centered at 0, 0. Then we go plus and minus 4 units in the z direction, just like we did before. And plus or minus 3 units in the y direction. So that's what this trace looks like. Well, in our 3D picture, the xz plane, or the yz plane, is back here. So it goes through at 4 for z and negative 3 for y, and 3 for y. You guys see it? You guys like M&Ms? To me it looks like a peanut M&M. It looks like a peanut M&M standing up and down. So let's look at the equation again. This is called an ellipsoid. It's longest in the z direction because that number under the z is the largest. And then we go plus and minus 3 units in the y direction and plus and minus 2 units in the x direction. So it's a little, it's most narrow in the x direction, and it's in between in the y direction. So here is the standard form of the equation of an ellipse, or excuse me, ellipsoid. Now we chose one that was centered at the origin, but this could be centered at any x naught, y naught, z naught that we want. Now we're not going to adopt the convention that a squared is the largest. We're just going to put the a squared under the x, the b squared under the y, and the c squared under the z. If that's equal to 1, all 3 variables are squared. All 3 terms are positive, and we have a 1 over here. We have an ellipsoid centered at x naught, y naught, z naught, and you go plus and minus a units in the x direction, plus and minus b units in the y direction, and plus and minus c units in the z direction from this center point to get points on your graph. And it looks like this. All 3 traces, the trace in the xy plane, the yz plane, and the xz plane, are ellipses. Here we're going to have traces that are ellipses as well, but instead of looking at the 3 coordinate planes, we'd look at the planes x equals x naught, and y equals y naught, and z equals z naught, so that the terms disappear, just like they did in that example. Now you can see from this that if the center is something other than 0, 0, 0, if it doesn't already look like this, you might have to complete the square. If you have an x squared term in a 5x, or a y squared in a 4y, or something like that, there are squares to complete there so that you can write this in standard form. In the next video, we'll look at the other quadric surfaces.